Hello, folks. Since we don't have class today, and we finished chapter 13 virtually yesterday, I'm going to go over the test I just posted. The idea is hopefully I will send you a digital copy of the test Thursday or so, or Friday. But normally, when we finish the chapter material, we'll spend a day or so going over last year's test. I just posted this last year's test on Google Classroom. Then I'm going to post this video. So, uh, if uh, if you will, maybe give last year's test a quick look through first, so I don't just spoil all the answers right away. But if you want to, you can just watch this video straight through. That's up to you. What we do on Friday, we'll have to see if we're canceled or not. But if we're canceled, expect another video of some kind or another. But so normally we'll spend some time looking at this. When I send you the test will most likely be something of a take-home variety, and so it's not going to be due for a little bit of time. So maybe a week or so when I finally hand it to you or send it to you. It can be done on any sheets of paper. Please, in fact, the digital version gives you the advantage of you do not, unless you have a printer, you're not going to be printing it out. And if you don't print it out, you can't make the number one mistake, which is trying to answer the questions on the test. But so let's go ahead and get started. I'm going to be switching in the DocCam from the DocCam and pulling the test away so we can work it out on a separate notebook. But okay, so let's look at this. The first thing, note, you may use any source except professors and or PhD containing individuals. Might also add in there AI, or if you use AI, you definitely want to show your work. The idea of some of these take-homes is that you hopefully get a better understanding for the material. But that's not to say there isn't some problems. So I want you to, rather than try to make you sit down and kind of like work it out in class, a bit more time, hopefully you will get a better understanding of the material. Because when it comes final time, we won't have all this time to work it out. All writing for short answer should be using your clearest handwriting or typing. If I cannot read it, I cannot give credit. Show your work for credit. That's kind of the most important thing. Circle your answer. I will give you partial credit based on work shown. So if you just have an answer and it's wrong, I cannot give you anything. If you have an answer and it's right, I may not give you full credit. But if you show work and I can see you got A, B, C, D, if you screw up on step B of a 5-step thing, I can take your numbers and follow it through and see, did you do all the other steps correctly? And then I'll still give you most of the credit. If I see the work and see how you got that, I say, like, oh, she wrote something down wrong. She added an extra 0. Well, that totally screws up your answer, but I can get the work from there. Plagiarism is discouraged. This is test version 1. I gave more than one version of the test. The problems are generally the same, but you're answering slightly different questions. So make sure you're answering the questions given. And don't turn in late. 5-point penalty for every day late. So Get it to me. Whether you have to take pictures and send it to me, get it to me. Okay, if for the following problem 1, if for the following compounds predict the following properties, will this compound hydrogen bond with itself? Will the compound hydrogen bond with water? And will the compound dissolve in hexane? So first thing is acetone. CH3, C, CH3. So I'm going to draw that. So we're talking about like a carbon, hydrogens, hydrogen, hydrogen, carbon, oxygen. When I say, will a molecule hydrogen bond with itself? What type of forces does it currently have? It has dipole-dipole and nonpolar interactions. There is a CO, which would give it a partial charge, the dipole-dipole. But for a hydrogen bond, you need a OH, an NH, or an FH. And there is no of those. So no, it will not hydrogen bond with itself. Now, if I added water to the mix, there's an OH. We could hydrogen bond with water. So yes, on step 2. Would this dissolve in hexane? Possibly. Hexane being, you can draw that out, it's just CH3, CH2, 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 CH3. This guy is nonpolar. This guy is very nonpolar. Like there's 3 carbons in a row. Shoot. Thing fell asleep. 3 carbons in a row. And so there's a good chance it will dissolve. Methanol. It is dipole-dipole, a little bit of nonpolar. Would this hydrogen bond with itself? Yes, it could. Yes on that. Would this hydrogen bond with water? Yes on the second thing. Would it dissolve in hexane? Poorly. Poorly on the hexane. We can look that up actually in the text, in the notes. We showed methanol and it showed the solubility in hexane is low. But you might be able to say yes, it will dissolve to some extent because it does have this nonpolar region. And then this final compound, CCH, Cl, Cl, Cl. This will be nonpolar, but largely organic. Will it hydrogen bond with itself? No. Once again, CCl, CH. Will it hydrogen bond with water? No. Because we need a O, N, or F. Cl, carbon, H, no O, no N, no F. So, X, X. Will it dissolve in hexane? Yeah, I'd say it will. It's largely nonpolar. There's a little bit of dipole-dipole. But chlorine is not superpolar. So, yes. So that's problem 1. Just asking you to think about some properties. Problem 2. Iodine has an enthalpy of vaporization of 41.57 kilojoules per mole, and a vapor pressure it creates is 760 torr at its boiling point of 457. So, I'm writing this down. Enthalpy of vaporization is 41.57 kJ per mole, a P of 760, a T of 457. And I ask, what is the P when the temperature is 373? And then a P when P is 159.9, what is the T? So this one's actually pretty straightforward. Mathematically, pain in the butt. The equation is ln P1 over P2 equals delta H over R 1 over T2 minus 1 over T1. R is 8.314 joules per mole Kelvin. Okay. Now, what is the easiest P to solve for? Easiest P to solve for is P1. The easiest T to solve for is T2. So we're going to choose those respectively to solve for. So problem 1, let's solve for P1. How do we do that? ln of P1 over 760 equals 41570 over 8.314. I converted this into joules. So since this is P2, 457 is my T2. And I'm just solving, just evaluating this. Just evaluating. So evaluating. 1 over 457 minus 1 over 373 negative 0.0049, we'll say 28. We multiply that by my 41570 divided by my 8.314. That whole left side becomes negative 2.46, we'll say 39. We take the second natural log, that's inverse log, and I'm going to put my answer in there. And so I have right now P1 over 760 is equal to 0.0851. Finally, times 760 is P1 is 64.67 torr. Now, I'm going to move this over here so I'm not too lost on my numbers. So, the second problem, ln of P1 over P2 equals delta H over R 1 over T2 minus 1 over T1. So this time, I'm going to use my 760 as my P1. And we said our P2 is 159.9. 41570, 8.314, 1 over T2 minus 1 over 760. Now, I could have just, not 760, sorry, 457. I could have just used my new pressure that I just found and my temperature 373, but instead I'm using my original. So you would have get it either way. So first, evaluate the left side. ln 760 over 159.9. You get 1.55, let's say 8. H over R. Next step, I'm going to multiply by R, multiplied by r, 8.314, and divided by my h, 4157D. It's going to give me a really small number. 0.0003117 is equal to 1 over T2 minus 1 over 457. Now, I'm going to add 1 over 457 to the other side. And so now we get 0.0024999 1 over T2. And then finally, I hit the inverse button. Inverse button is the x to the negative first button. And that's going to flip the T2, 1 over T2 to T2. So T2 becomes 400 Kelvin. And so I have my values. So when I went from 64.6 torr to 159, it only changed by mere 27 Kelvin. But it's an exponential increase. It's an exponential increase. So with that in mind, that was this problem. Not impossible, but yes, a pain in the ass. Okay. Looking at this. What is the molecular formula of the following crystals? So I try to hint that, try to give them in color when I can. So these are my O atoms. These are my copper atoms. So look into the O. O is in all the corners. Remember, corner is 1/8. So there's 8 corners. So there's 1 oxygen atom, and this is a body. So how many total oxygen atoms? We have a total of 2 oxygen atoms. 2 oxygen atoms. Now, because of where this is at, these are body but in the corners. Bodies but in the corners. So with that in mind, 1, 2, 3, 4. There's 4 here. So my molecular formula is a 4:2 ratio, so Cu to O. Cu2O. Now with that in mind, so that's that guy. The black atoms, or in this case, since it's in color, you couldn't really tell. But these are the titaniums. These are the oxygens. I gotta scroll this up. So you can see, it's a really freaking complicated looking structure. Now, notice, this is the bar. So with titanium, corners, looking at this, these are on the face. It's really hard to tell, but these are in the face, body. Each face is worth a half of an atom. So 1, 2, 3, and the body makes 4 titaniums. These guys are in the edge. These guys are in the edge. So, and this guy's in the face, edge. This guy is in the face. It's not quite on the edge. So the face, then we have a body and a body. Face. Okay, looking at it. Edges. Edges are worth a fourth. 1, 2, 3, 4. That's 1. That's 2. So 2 from the edges. This is a really hard one. 1 atom. There's 2 atoms. There's 3 atoms. There's 4 atoms. 4 from the face. And 2 full ones from the body. So 6, 8. 8 oxygen. So that structure is TiO2. It's a really complicated guy, really challenging one. But remember, you should have a simple ratio most of the time, a simple reducible ratio. So if you're getting something like, well, there's 7 of those or whatever, you probably made a mistake. But that is probably the hardest one related to that. Okay, looking at that. The solubility of gas. Oh, please note, I did include a useful information sheet. All the equations that we saw this chapter. So you are not expected to memorize them. They would have been given. So the solubility of a gas is determined by Henry's law. If a solution of carbonated water is stored at 276 kPa, answer the following questions. The value cannot be determined. Make something up to use on further parts, stating that you are doing that. So basically, if I need part A to solve part B, and I at a loss for part A, make a value up. Say, oh, I don't know part A. I say A is 5, and then work out part B with A, and then go from there. And I can work it out. That's the beauty of this. I can work it out. So, Henry's law states that molarity, which is solubility, is equal to Kh times the pressure. How do we know that? Well, it's given, and also Kh is in units of 3.3 times 10 to the negative 7th molar per pascals. Pressure is 276 kilopascals, or 276,000 pascals. So with that in mind, problem 1, solve the molarity. Pretty easy, actually, but some people got at a loss. Figure out what equation is Henry's law and how to do that. So it's literally, you're just multiplying those two numbers together. 3.3 times 10 to the negative 7th times 276,000. So what is our molarity of carbon dioxide? What is our concentration of carbon dioxide? So easiest way to type this in on a calculator like this is hit second E negative 7, and then I'm going to multiply by 276,000. So my concentration, my molarity, is 0.09108 m. Okay. What is the molality if the density, so the density is 1014 grams per milliliter? So molarity is defined as moles over liters. So one way to look at this is 1014 kilograms per liter. That's a convenient conversion. 1,000. So, how much will our solvent weigh? 0.09108 moles per liter. Well, 1 liter weighs 1014 kilograms. So this is actually we're not going to do it like that. We're still going to keep that. But what we're going to do instead is we need to figure out, we're going to make an assumption. We're going to assume 1 liter. Okay, that's going to make it easy. So that means the moles is 0.09108 moles. How much does that weigh in kilograms? Well, the molar mass of CO2, 1 mole of CO2 weighs 12 plus 32, so 44 grams. So 0.09108 times 44 is 4007 grams. Now, if I have 1 liter, that means I have 1.014 kilograms of solute. So I'm going to subtract out 0.004 kilograms. So my solute is 1010 kilograms of solvent. Solution, solute. So, taking my original 0.09108 moles, dividing that by my 1010 kilograms, this will give me my molality, 0.09108 divided by 1.01, that one. See, that's an easy thing. I typed it in wrong. Means we have a molality of 0.090, we'll say 18 moles. Sorry, not moles, but molality. Finally, last question. How much would the freezing point decrease if the Kf is 1.86? Now, delta T is equal to negative I Kf m. Now, even though this is not quite correct, we are going to make the assumption that CO2, the I is 1. Now, in reality, carbon dioxide forms carbonic acid, which will split up to some extent, but we don't know that. We don't know what the extent that is, so we're going to just do it like this. So 0.09018 times 1.86 means my freezing point will not be at negative 0. It will not be at 0, but it'll be at negative 0.168 degrees Celsius. It was dropped a small fraction. Not much, but it has dropped a little. A lot of work for very little payoff, but sometimes that be how it be. Now, phase diagrams. Looking at a phase diagram, we need to know things like this is my triple point, this is my critical point. What is my units? This is Celsius, so we got to add 273 to all these things to get them into Kelvin. And this is an atmosphere. Notice it's a logarithmic scale. So estimate the critical point. So that's the hardest thing. We'll say maybe 70 atmospheres. And so each of those is 10, so that's negative 110. So adding that to 273 is what, like 163 Kelvin? Give me something close. Give me something close. That's all I ask for. Give me something close. If you come up with the exact number, I'll know you used up. You looked it up online. I don't want you to do that. I want you to read the damn graph. What phase change is the first to occur upon a decrease in temperature from standard temperature and pressure? So STP, if I'm going to the first thing that's going to happen, it's going to liquefy. It's going to condense. Condense. What phase would occur if you decrease the pressure? Nothing. No change. If you increase the pressure, it would go to a supercritical. But when you decrease, the gas stays a gas. Now, this one is, okay, we're looking at the IKBM. They're all the same molality. They're all going to be at the same KB. The only thing that can change here is my I. So we're looking at which of these guys are ionic, and then how many ions would they produce. So sodium, chlorine, ionic, I of 2. This is non-ionic. It's sugar. Non-ionic. So I of 1. Ionic, 2 plus, 2 minus, still an I of 2. Ionic, but the I of 3. So which one of these would split up the most? Sodium carbonate. Easy enough. Last 2 problems. 7 is a long one. 8 is not exactly the best one. So, but the idea is, like, I could ask. Okay. So, show the conversion of 1 liter of 68% by mass nitric acid with a density of 1.41 grams per milliliter. Turn it into molarity, molality. Find the osmotic pressure and then the boiling point elevation. We want the osmotic pressure at 298 and the boiling point elevation if the KB is 0.512, and we're going to assume the I is 2. That it forms H and NO3. So, 68% by mass. 68% by mass means 68 grams in a 100 gram solution. No matter what, 68 grams, we need to turn this into mole. The molar mass, H is 1, N is 14, 16 times 3 is 48. 48, that's 50, 62. So it's something like 63 grams in 1 mole. So no matter what, we need to do this part for both A and B. 68 divided by 63 is, we have something like 1079 moles. Okay. 1079 moles. Now, if I'm doing molarity, I have to turn grams of solution to liters of solution. So we're going to take 100 grams and divide it by 1.41 grams per 1 milliliter, and then say there's 1,000 milliliters in 1 liter. So 100 divided by 1.41 divided by 1,000 means we have 0.070 9 liters. So 1079 divided by 0.07092, or 079 divided by 0.0709, a molarity of approximately 15.2. Pretty dang high. Then again, 68% is a lot of nitric acid. It's concentrated. So we're still going to need that value again. But now we have 100 grams. That's solution. How many of it is solvent? So I'm going to take away my solute. That means we have 32 grams of solvent, which is 0.032 kilograms. My molality would be my 1.079 divided by my 0.032 kilograms. So my molality is going to actually be quite a bit larger. Something like 33.72 molal. So, wow, that is pretty concentrated. Osmotic pressure. So, that was B. Osmotic pressure is defined as I times M times R times T. We said I was 2. Assume I is 2. We said M was 15.2. R needs to be in units of our gas, and T is, we were told, use 298. So this gets us into atmospheres. You could absolutely use the one to put in bars. I really don't care. 2 times 15.2 times our R times our 298. What's the osmotic pressure? 743.4 atmospheres. That is a crushing pressure. Most things, if you put that in there, will die. That is incredible pressure. Now, for freezing point depression, or actually boiling point elevation in this case, I times KB times M. Said I is 2. Even though KB is really small, M is really big. So 2 times 0.512 times 33.72. The new boiling point, the boiling point has gone up by 34.5 degrees. So our new boiling point is 134.5 degrees Celsius. That is our new boiling point, because this only calculates our delta T. Boiling point of water is at 100. So there is that massive problem. Not necessarily hard if you can break it down, but it seems very intense. Now this last one is a little bit more of a problem. So, not my best problem. Interesting one. Everclear is a high purity green alcohol bottle in various ethanol to water ratios. Bottled in various ethanol to water ratios. The bottle of Everclear contains 60% alcohol by volume, which is a 54.26 mass percent. So I've done the conversion for you. What is the mole fraction of ethanol to water? Given the pure vapor pressure of 3.157 kilopascals of water and 7.929 for ethanol and Raoult's law, what is the total vapor pressure the mixture would give off? So A. So we got to find out mole fraction. 26% alcohol, which is C2H6O per 100 grams. So, with that in mind, that means there would be 45.74 grams of water. That's the kind of tricky part and get us started. Look up what is ethanol. Find out the formula of ethanol. Figure out what is missing to get the water. So what is the moles of water? 18 grams per mole. So 45.74 divided by 18 means we have something like 2.54, we'll say 1 moles of water. And ethanol, 12 times 2 plus 6 plus 16, 20, so 24 plus 6 plus 16 is 46. So I'm going to divide this by 46 grams per mole, and that's going to give you, divided by 46 is going to be 1.17, we'll say 96 moles of ethanol. So what is the mole fraction? Mole fraction of, so chi of, we'll say ethanol, is going to be 1.1796 divided by 1.1796 plus 2.541. 0.541 puts us at 3.7206 on the bottom. So 1.1796 divided by 3.7206 is mole fraction of 0.317, we'll say O, for ethanol. So the remaining for water would be 1 minus that. 6.830. So we can go to round off those zeros. Okay, so we had the mole fraction of ethanol, the mole fraction of water. There we go. That's A. B. Raoult's law says the P of ethanol is going to be equal to the pressure pure of ethanol times its mole fraction. So the pressure of ethanol is 7.929 kPa, and the mole fraction is 0.317. 7.929, 0.317 equals 2.51, we'll say 3 kPa. Now, water is be done the same way. P of water is going to be equal to the P star of water times the mole fraction of water. So that's going to be the mole fraction of the pressure of pure water is 3.157, and our mole fraction is 0.683. 3.157, 683 is going to give you, oh, I did something wrong. No. Oh yeah, I divided. I didn't multiply. 2.156 kPa. Now you notice, I noticed something was wrong right away because I got a number that's bigger than the multiplication. Like, oh, when you multiply by something by less than 1, you should get a number less than you started with. So I knew something was wrong. So the total pressures is the sum of that. So we're going to take 2.156, and we add 2.513. Total pressure 4.669 kPa. I think that's enough to give it, what is the total vapor pressure? So, boom. I'm going to give a reduced vapor pressure of 4.669. Now, while I did not ask this of you, what percentage or what was the fraction of it would be from the alcohol? So I'll take the 2.513 and divide it by 4.669. Something like the fraction that's in the vapor phase is about 50% as opposed to the 30%. So if someone took a shot of Absolute Everclear and breathed on you, you'd be able to tell it's highly concentrated alcohol. Big old burst of that. But okay, so that was last year's test. I know I went through it somewhat fast, but the advantage of this is you can rewatch, you can pause. I have all the work here. So, either way, take your time. You have a week. I didn't say you can't work with other students, but just make sure you're answering the questions you're given. I can easily get another phase diagram and give you someone a completely different phase diagram or ask different questions or the same phase diagram. So make sure you're answering your questions because I'll know which one I gave you. But with that in mind, have a good day.